Hello friends, I Prof.Darshan Thakur from Terna Engineering College Dharashiv welcomes you on my YouTube channel for this subject head Control System Engineering. Friends, as far as our today's session is concerned, so we will try to learn the important analogous technique which is used in case of this mathematical modeling of control system, whose name is nothing but the force voltage analogy, right? So first of all, we need to understand the objective behind this force voltage analogy, right? Basically, there are two different types of analogous techniques we are having with us. Their names are nothing but the force voltage analogy and the force current analogy, right? So the objective behind these two analogous scheme is to obtain the system equation of that given control system when it is described is in terms of mechanical form, right? So in case of this mechanical type of control system, we are very much aware of this thing ki there are three basic elements of that mechanical system. These three elements are nothing but what? The mass, spring and damper, denoted by this capital M, K and capital B, right? So similarly, whenever we are mapping that given mechanical system is in terms of electrical system, so as far as this electrical system is concerned, so these are the three basic parameters of this electrical system: resistor, inductor and capacitor. So by the virtue of these three parameters, this force voltage analogy is being used. So let us quickly go through the basics of this force voltage analogy. Initially, we need to consider this circuitry in which these three elements are connected in series form. As these are connected in series form, so the similar current, the suffix I flow through this resistor, inductor and capacitor whenever that circuit is being excited with the help of this external voltage or the input voltage denoted by V of t, right? So in order to analyze this circuit, we need to apply this circuit analysis law, whose name is nothing but what? The Kirchhoff voltage law, right? We need to apply this Kirchhoff voltage law to the circuitry. As a result of this, what will happen? We are supposed to, because this Kirchhoff voltage law says that the summation of ohmic drop across each and every element equated to 0. So as here we are having three different elements, we are supposed to determine the ohmic drop across these three elements, and the summation of these ohmic drops are being equated to 0, right? So when we start our journey with this input voltage, right? So as we are going from negative plate to positive plate, its polarity will become plus V, so it will become plus V of t. When we map this resistor, inductor as well as capacitor, so what is important for we people in case of this Kirchhoff voltage law is to follow the direction of assumed current. As the direction of this assumed current is in clockwise direction, so obviously these three parameters are connected in horizontal arm, right? So if these three parameters are connected in horizontal arm, so there will be only two, the probability of circulation of current through these horizontal parameters is nothing but what? Either right to left or left to right. But according to the assumed direction, this current flow through this resistor from left hand side to right hand side, through this inductor from left to right, through this capacitor from left to right. So this polarity plays a very important role in case of this Kirchhoff voltage law in order to decide the overall polarity of this ohmic drop across R, L and C. So accordingly, the ohmic drop across this resistor, according to that Ohm's law, V equals to I into R. So which current flow through that R? I. So as we are going from positive plate to negative plate, the overall potential will become negative. The same concept is used in case of inductor. The voltage across inductor will be what? The ohmic drop across this inductor will be L di by dt. Similarly, the voltage drop across this capacitor will be 1 over C integral of I of t into dt. That we need to recall the ohmic drop across these two energy storing devices, right? So again the negative sign we need to consider, so it will become L di by dt. Again minus sign we need to consider as we are going from positive plate to negative plate. Ohmic drop across inductor 1 over C integral of I dt, right? Then the same equation can be rewritten is in terms of V of t, so it will become IR plus L di by dt plus 1 over C integral of IDT, right? Now according to the basic definition of this current, I is nothing but what? The rate of change of charge per unit time, right? Here this I is replaced as a dq by dt. The rate of change of charge per unit time is nothing but what? The desired value of current, right? So when we substitute the desired value of I into this existing statement, so this statement will become what? V of t equals to R times of dq by dt plus it is di by dt. When this I is being replaced with this dq by dt, so d by dt into d by dt, it will become L into d square q upon dt square plus 1 over c. The expression is like this, integration of I into dt. When we replace this I with this differentiation operator dq by dt, so these two opposite operator will cancel each other, so remaining thing is nothing but what? Q, right? So if suppose we are calling it as the equation number 1, and for sake of our convenience, when we apply the Laplace transform to this equation, so it will become what? V of s equals to R into, as we are having the first order differentiation, so Laplace variable for first order differentiation will become s, so Rs into Q of s plus, as we are having the second order differentiation, so it will become Ls square into Q of s plus 1 upon c into Q of s, right? Then another important thing which we need to remember, as this I is being substituted with this value, the rate of change of charge per unit time, if we apply the Laplace transform to this statement, it will become what? I of s equals to s times of Q of s, right? So whenever we are having this term s into Q of s is being replaced with this I of s, I will put this quantity in this rectangular box. So as far as this equation number 2 is concerned, if suppose this is equation number 2, right? So in this equation number 2, what we need to replace with which term? I of s equals to s times of Q of s. As a result of replacement, this equation will become what? V of s equals to what? S into Q of s is nothing but I of s. So R into I of s plus s into Q of s is nothing but I of s. As we are having s square, so it will become Ls into I of s plus 1 over c into Q of s. Here we don't have this s term, so it will get divided with this c. So 1 upon c into s into I of s. So this is nothing but what? Equation number 3, right? So this is nothing but what? The s domain representation of this KVL equation, because as far as this KVL is concerned, so the same current I flow through this R, the same current I flow through this L, and the same current I flow through this capacitor C. Here also the coefficient of R is nothing but I of s, capital I of s. The coefficient of L is nothing but what? S times of I of s, means the similar current flow through this inductor, and the coefficient of this 1 over c, elasticity, is nothing but what? Again here I of s, right? So when we compare this equation number 3 with the basic mechanical parameters, right? The force equation for this M is nothing but what? The force equation for this M is nothing but what? L square into, the force equation for this M or for this mass is nothing but what? M followed by d square x upon dt square. The force equation for this spring is nothing but what? K into x. The force equation for this damper, which will try to oppose the flow of motion, is nothing but what? B into dx by dt, right? Means to that mass, second order differentiation we are having in that force equation, right? To this damper we used to have the first order differentiation, and to this spring we don't have any differentiation sign out there, right? So as a result of this, when we compare this equation number 3 with the force equation is in terms of s domain, right? The force equation in terms of s domain will become what here? M s square into x of s, here k into x of s, here bs into x of s, right? So we will come to know ki as we are having the second order Laplace variable s square associated with this capital M, means stands for M stands for what? The mass, right? So when we compare this equation number 3, when we compare this equation number 2 with the force equation of these three mechanical parameter, so we will come to know ki M is analogous to L. Why? Because to this L we used to have the second order Laplace variable s square, right? In its basic definition, how the force equation for that mass is represented m into d square x upon dt square. In its s domain it will become ms square into x of s, right? As far as this damper is concerned, so to that damper we used to have the first order differentiation, because this frictional force is directly proportional to velocity, the rate of change of displacement per unit time, right, denoted by dx by dt. So in this equation number 2, the first order Laplace variable associated with which electrical component? It is associated with this electrical component, called it as R, right? So this B is analogous to R, right? Then the third mechanical element we are having with us is nothing but what? K. We don't have any Laplace variable, or we don't have either first order differentiation or the second order differentiation in its force equation, right? So its force equation is nothing but what? K into x of s, right? When we compare this k into x of s, so we will come to know ki we are having one term which is nothing but what? 1 over c into q of s, right? Here this x is nothing but what? The displacement, right? X is nothing but what? Displacement is analogous to this charge. That is nothing but what? Q, that we need to understand, right? So 1 over c is analogous to which mechanical element? Spring. So this k is analogous to 1 over c, and this force is analogous to voltage, and this which parameter? This displacement is analogous to charge, right? So this is how the system equations are to be defined. So in this way, the force voltage analogy is being used to convert the given mechanical system into equivalent electrical system by replacing this M with L, by replacing this B with R, by replacing this K with 1 over C, by replacing F with voltage, force with voltage, and this displacement with this charge. So these are the analogous term. These are the analogous electrical term belongs to this mechanical term, right? This Q is analogous to X, L is analogous to M, R is analogous to B, 1 over C elasticity is analogous to spring, and B is analogous to F. So each time we need to use these three analogous term along with this displacement is analogous to charge whenever we need to convert that mechanical system into the electrical system. Thank you.